So, ladies and gentlemen, welcome to this lecture, part of the sustainability series, tonight with Christophe Bonnal, a long-time space debris and launcher expert, now at MaiaSpace. He will tell us what MaiaSpace is. About something that is growing as a topic, space pollution, space sustainability, with the title Towards a Sustainable Space, addressing the challenges of the final frontier. My name is Olivier Dessibourg. I'm a science journalist here at the Swiss Public Television, RTS, and I have the pleasure to moderate this event. After Mr. Bonnal's presentation, we'll have a discussion. And for that discussion, you may ask questions, not with the microphone, but directly by writing them down. And for that, you will need to log in on a web page. It's simple. You just scan this QR code, and you get to the web page. And there you can either write your question directly. You can also, please do specify if the question is addressed to one of the speakers in particular. And you can also rate other participants' questions by liking or disliking the question. And of course, I will take the questions that have the more likes first. So please do that anytime from now. While Christophe Bonnal is presenting his presentation, while we are talking for the roundtable, and of course during the Q&A session at the end. You will see the QR code again, so no worry if you don't have, if you haven't scanned it yet. Just an important notice is that no data at all is recorded here, so feel totally free to ask your question to the speakers. Before that, we'll have a discussion. As said, we'll have the presentation, but even before that, now I have the pleasure to give the floor to Emmanuelle David, the director of the EPFL Space Center, for a welcome address. Please.
Good evening. My name is Emmanuelle David. I'm Executive Director at EPFL Space Center, which is the unit that pushes space-related research, education, and innovation at EPFL. I'm really glad that we are hosting this event on space sustainability. We've been working actually at EPFL over a decade on space sustainability with the first mission Clean Space 1 that then led to the spin-off, creation of the spin-off Clear Space. That was awarded in 2018, the first contract from the European Space Agency to remove space objects, and which is continuing the development and should launch by 2027. At EPFL, we look at space sustainability in a holistic manner, really looking at what are the environmental impact of space activities on the Earth and space environment, from early design phase and to production, launch, operations in space, so which is also space debris, and during re-entry. On that, we do in concrete manners. We have launched a professional course on space sustainability, which second edition was this year. We have also started this semester a class for master students, and we have some of the students here, so I'm really glad that they are there. We also work with EPFL associations to challenge the students on how to develop more sustainable missions, so with the rover team, the spacecraft team, the EPFL rocket team, for example. And we've published also guidelines for moon sustainability, and we're working also on a handbook for eco-design. And also, finally, we have one key project, which is also on early mission design life cycle analysis. And while working on this project, which is funded by the European Space Agency since 3 years, it really came out that one of the big knowledge gap is what are the impact of space activities on the atmosphere during launch with the launcher, but also during re-entry. We believe, so in the space community, there is a big thoughts that to solve the issue of space debris, you need to re-enter these objects. And actually, this brings also other questions and other issues. And I'm really happy that today Christophe Bonnal will be there to address this question. I'm really glad also that we have our distinguished panel. So thank you very much for being there. It's a unique opportunity to have all those experts also talking and exchanging together. So I'm glad, and the audience can be there also to be there to see this nice discussion. I want also to thank Mediacom for organizing this event with the communication, but also the recording, and you will be able also to see after the recording that will be published on our YouTube channel. So this event is part of the Sustainability series from EPFL. So you can see that today we talk about space, but there was a lot of other thematics. What is the future of skiing, the impact on the Red Seas, and today we bring you in space. Thank you very much, and I would like to welcome on stage Christophe Bonnal, which actually is a long-lasting mentor of mine that did give me a lot of help when I did my master thesis back in 2010, 9 or 10. So soon we'll celebrate 20 years. When I was looking actually on how to remove NVSAT, to do active debris removal from NVSAT, and NVSAT at that time was still an active satellite. Now it's not an active satellite anymore, but it's still a satellite that is up there in sun-synchronous orbit, which has the size of an English bus, and no one has gone there to remove it, so it means the topic is still very actual. Thank you very much, and let's welcome Christophe on stage.
Thank you very much, Emmanuelle, for these kind words, and really it's such a pleasure being with you, having the privilege of being here. I love this place. And so thank you, Emmanuelle, thank you, Jean-Paul. It's a pleasure seeing Claude as well, as usual. So today I'd like to present an idea which is not a classical idea. It's a little bit different from what we hear usually. It's not a conventional, I would say. It's a kind of question that we have compromise between two situations. So I'd like to show it to you. First, I'd like to introduce Antoinette Haute, who works very nicely with Emmanuelle for UCAS, for instance. Antoinette is our engineer devoted to environment in MaiaSpace. MaiaSpace is a startup devoted to a small launcher, 300 tons, but to a launcher, and we are very, very focused on being clean in terms of, so we really have all the life cycle assessment ready, and launch with biomethane and reusability and so on and so on. Every step is cautiously watched out by Antoinette, and she yells at us as soon as we do something wrong. Okay, so let's say, first of all, something which is obvious. Let's say, anything that is launched in low Earth orbit, let's say up to 2,000 kilometers, will re-enter atmosphere. Anything, everything. Yeah? First, because in terms of international text, you are not allowed to raise the orbit above 2,000 kilometers. So anything will re-enter either in a controlled way, voluntary, and with retrieval. For instance, when we launch Claude, we try to retrieve his spacecraft. Okay, but then it can be so it can be a controlled reentry. It can be a random reentry, uncontrolled, which is unfortunately the case in 90% of the cases. So anything, anyhow, will re-enter, and very few is recoverable future potential reuse. This is nevertheless an axis on which we are working, how to recover the stages, how to reuse them. And for instance, in Maia, we're studying about the reusability of the first stage, of course, but of the second stage, the orbital stage as well, and it's quite complex. In terms of random reentry, it can be either following a delta V, aiming at a perigee which is low enough to be captured by atmosphere, typically 50 kilometer or 70 kilometer, or it can be just a re-entry following the drag from the residual atmosphere. So in this case, when we have an atmospheric drag, a re-entry, then one of the things is it leads really to a random re-entry with an area. The area of the re-entry is somewhere between plus or minus the inclination, which can be quite wide, okay? And with a typical precision of 10% of the remaining lifetime. So it means 10 days before the re-entry, you know that the object will re-enter in 1 day. 1 day is 14 orbits. So you know that it will re-enter plus or minus 14 orbits, which is, so it means you have no idea at all where it will re-enter. The day before the re-entry, so 24 hours before, then you're confident it will re-enter tomorrow, plus or minus 2 hours. That's plus or minus 60,000 kilometers. So you know where it will not fall, you don't know where it will fall. And that's a very hard time. For instance, I know that I have a lot of debris, maybe even ones that I launched, that will fall on Paris tomorrow. And so when I tell the authorities, be careful, we have a 5-ton debris re-entering on Paris tomorrow. Oh, are you sure? Oh, quite. Plus or minus 3 turns, 3 rounds over the Earth, so which is not real serious. And so it's really a Damocles sword, and we need to solve this equation rapidly. So for this, we have plenty of dedicated tools to estimate. It should work, this. Yeah, to estimate the orbital lifetime. I just quote a color of one. During then the re-entry process, typically we have a couple of phases. First, above 120 kilometer altitude, nothing real happens. There is no atmosphere, or really hardly any atmosphere. There's still always a little residual atmosphere following a negative exponential versus altitude. But 120 kilometers, this is the classical value of the reference altitude for the re-entry. Then we have a breakup due to dynamic pressure, which is proportional to the square of the velocity, somewhere between 90 and 70 kilometer altitude. Okay, so you gain the drag, you gain the structural dismantling, first the solar panels, the antennas, maybe the box itself. And then following this, you have a partial burn-up due to the atmospheric friction, which is V to the power 315 or something. And so this means that the objects will encounter very high temperatures, typically 1200, 1300, 1400, 1600 degree. And so it means that it will melt. More or less everything will melt except the objects which do not melt, and we'll just see it after. Typically, we have 5 to 30% of the mass which survives the re-entry. So it depends on the manufacturing of your objects. Okay. So for this also, we have some dedicated tools to estimate the demise process, including a very good one from EPFL, by the way. Here is a typical re-entry. So you see here this is what I saw from a plane with the re-entry of the Ariane 503 flight way back in '98, I think. And this is an illustration from the aerospace. Okay, so you have first during the re-entry, first the breakup, then the heat phase. Okay, and what survives goes into the ground footprint. Here is a re-entry. One example of a re-entry. Here you see the Big Dipper behind here. So this is a Chinese Long March 7 upper stage. And the nice thing is that this is Los Angeles. So you see, this is a kind of conjunction that can be quite... these kind of examples, we have thousands of them because we have so many automatic cameras filming everything all the time nowadays. And so here you have Cassiopeia. Okay, and so these kind of videos, we have plenty of them. This is really typically what we have. Just for fun, we can do some spectroscopy.
I got it.
Spectroscopic analysis of what's re-entering. And so we can see exactly
Wow.
what is melting, if it's aluminum or whatever. For instance, during the ATV re-entry, one of the ATV re-entries, we could see the urine of the astronauts. Okay, so it had a special signature. Okay. So what survives is typically 4 kind of items. First, the refractory materials. They are meant to survive high temperatures. Titanium, stainless steel, some carbon, some CFRP, the famous COB-V, carbon overlaid pressure vessels. Here is an example. This was a PSLV upper stage, a CFRP tank, which was recovered on ground. So, second thing are the dense material. They should melt, but they don't have time to melt completely before impacting the ground. And this can take, the re-entry itself can take 20 minutes. But so the phase of melting is too fast. And so, for instance, if you have a nice turbopump of an engine, it will start melting, but you won't have time to melt it completely before it impacts. Here is an example. This was an ISS battery sport. It was famous quite recently. Was it one and a half year ago? It punched through the roof of a house and ended in the room of a kid who was a little bit surprised. Okay. Then we have what we call the Russian dolls. These are the structures that are intricated one in another. So you have a first wall that will disappear, melt. Okay, then you attack the second wall, which will be heated and progressively disappear. Then you have the third wall, and so on and so on and so on. And you don't have time to melt everything before it hits ground. Here is an example. This is the remains of a SpaceX Falcon 9 computer. It did not melt completely, despite the fact that individually each card should melt. But we found it like this. By the way, it's highly confidential and secret and ITAR and all the stuff. But okay, it's not really reusable. But we learned quite a lot about the redundancies, and there are the connectors and the backface, and so we learned quite a lot. And the last thing are what we call the dead leaves, which are objects with a very high area to mass ratio. So they're very light, very large, and so they are slowed down at very high altitude. And then they are slowed down, and then they just fall with a low velocity without seeing the heat flux. This is, for instance, this is Mrs. Lottie Williams. She is the first person, the only person, to my knowledge, to have been hit by a debris. But she was quite lucky. It just fell on her shoulder. It was smoking, so she took it to the sheriff, who took it to NASA, and they identified that it was a piece of a thermal protection of a Delta II stage. So these are the kind of objects that survive. Yep. Here. Plenty of examples. It's always funny. This is a sphere, a high pressure sphere from Ariane that spent 19 years in space before re-entering on ground. I had it in my office for quite a long time. This is a piece of Long March 5. This is some Delta II. What do we have? This is a Vega propellant tank. Okay, and this is a special SpaceX page. These are only Falcon 9 objects. Okay, so the high pressure, the COB-V here, carbon fiber wrapped, and they damage plenty of things. Okay, so these are the examples of what we have. Clearly, these objects could kill someone on ground if they hit ground. A surviving element can have a direct impact, or indirect impact. We always quote the fact that it could fall on railway tracks and cause a problem to a train, or fall on a chemical plant and kill everyone around. Okay, so we have plenty of methods to compute the risk of a re-entering object. Typically, what we say is a debris becomes potentially lethal if its energy is higher than 15 joule. So 15 joule, don't play tennis, because it kills. It would kill you. 15 joule is, I think that a good service, it's 100 joule. So 15 joule. What we have at international level, we have some rules which are correctly shared, which give us a right to kill, okay, James Bond, a right to kill of 10 to the minus 4 per re-entry. We consider, so when we do all the computations, we end up with the probability of killing someone on ground during a re-entry. If this probability is lower than 10 to the minus 4, then you can let the object re-enter randomly. If it's higher than this, then you should be careful, and you should either do a controlled re-entry, for instance, falling in the South of Pacific, or change the design of your element. So we've tested plenty of things, for instance, in the DLR high enthalpy tunnel, where we pass some classical elements. Here you recognize a battery. So this is after a simulated re-entry. So battery does not melt. This is the kind of thing that can survive. You have some structures that can survive. We checked the inertia wheels, which are very dense, can survive re-entry, electronics, and so. By the way, there was a recent controversy which was raised by the FAA in US based on studies led by the aerospace. And the aerospace, I don't know if you're familiar with the aerospace, but they are very, very professional in re-entry. They've been doing this for ages. And when they say something, you listen to them. And so they estimated that just the re-entry of the Starlink satellites integrated over the complete constellation, so integrated over typically by 2035, this would lead to a risk of killing someone of 60% each year. Okay, and so that's because you have the risk is tiny, multiplied by 10,000, so this gives you a 60% risk of killing someone. They computed also 0.07% risk hitting a plane in flight. So of course the probability is much lower, but the effect can be significantly higher. But then this was highly contested by SpaceX, who said quite realistically, you don't know our satellites, so how could you make these computations? We contested. Our satellites melt completely at re-entry, or nearly. I like the little bimble. Okay, they nearly melt completely. So we suspect, nevertheless, the batteries may survive partially. They have an electric propulsion, and so the electric propulsion, the engine, is based usually over a magnet, which is very dense and which probably survives re-entry as well. So these are the elements. But, okay, this is one of the questions. So out of this, the natural tendency, and the one which is well known today and specified in the standards, and so is this notion of design for demise, D4D. If you design a satellite, please, or a launcher, please be sure that it will melt completely at re-entry and not be dangerous. Okay, so if you have the choice between a tank in aluminum and a tank in titanium, please choose aluminum. It will melt at re-entry. So this is the classical design for demise, selection of architecture and materials. Okay, so that's the situation. Until someone realized, hey, if there are 5 to 30% of the mass which survive re-entry, it means that 70 to 95% of the mass remains in high altitude, vaporized in high altitude. Vaporized, be careful, the words, I don't know which word choose. And it's a complex word because is it melting? Is it burning? Is it sublimation? Is it vaporizing? Let's say it's all this in a package together because so there is most of the mass will remain in orbit. For instance, my upper stage on Ariane 5 is 5 tons. Okay, I know that out of these 5 tons, 1 ton will survive. It means that every upper stage of Ariane that re-enters leaves 4 tons in the air. So in the upper atmosphere. This leads to plenty of questions about gas chemistry. During the re-entry, you have a shock wave which dissociates the air in front of you, and so which generates the nitrogen oxides, mainly around the 50-kilometer altitude. This high-speed re-entry also generates chlorine. We have some metal oxidation reaction, mainly aluminum. Aluminum, which is something that we like. For instance, on my 5-ton stage, I have probably 4-ton aluminum or 3 tons aluminum. And they love at re-entry to melt, to burn, and to combine with the residual oxygen there, and to combine and to create alumina. And alumina is a very, very good element to kill the ozone layer. We have the sublimation of alloys at sufficiently high temperatures, such as copper, zinc, titanium. I mentioned a study which is very interesting from NOAA, where they had an experimental plane, a high-altitude plane, WB 57 from NASA, sampling the atmosphere up there. And they found plenty of materials that should not be there. Mainly, for instance, plenty of niobium, okay, or columbium, and which is typical of the nozzle of the upper stage of Falcon 9. And so clearly the upper stage of Falcon 9 leaves some niobium, columbium in the upper atmosphere. So the question is it dangerous or no? We have no idea, of course. So we have every element that composes our satellites and launchers. We found them up there: copper, zinc, titanium. Then the strange thing also is that these elements, so let's say, I don't know, a piece of copper will vaporize, creating some small particles. What is the size of these particles? One micron, much less, much more. But the strange thing also is that they will quickly recombine with the residual atmosphere elements to create some aerosols. We can have some aggregation with sulfuric acid particles. And then we have the wind that transports these gases and particles mainly towards polar regions. And it's quite strange because spontaneously you say, okay, these particles should fall. And so when you look at the diagram and when you look at the analysis, yes, they fall until they are caught back in a swirl at polar latitudes, re-injecting them in higher atmosphere. And so it's really complex. These objects may remain quite a long time in orbit. One thing also which is very important is the behavior of carbon at re-entry. It can generate what we call black carbon, which is the soot. And the soot is an extremely powerful element for the warming process. So this is globally the kind of behavior, what's becoming of the materials that re-enter. And then we have plenty of, it's funny because when we are working on these topics, I found that there was absolutely unanimity among all the specialists. They are all unanimous to say we know nothing. And we have to study it, and we need to understand better. And so this is current situation. So we see that the aluminum can lead to formation of stratospheric clouds in polar regions, which release some chlorine, which accelerates the ozone-destructive reactions. Probably also other metal cations could also affect these clouds. Black carbon contributes very, very strongly to stratospheric warming, accelerating also the ozone depleting reactions. The nitrogen oxides are very critical also. But we must admit here are what I call the knowledge gaps. There has been a lot of studies, mainly about the rockets, the launchers, much less on spacecraft. It's easy. It's only because rockets are much simpler objects. You have basically large tanks made of one material, and so spacecraft are always more complex with plenty of different materials and so. It's difficult also to differentiate between meteoritic and anthropogenic materials, okay? Because of course there are plenty of meteorites, and so if what I'm complaining about here is completely minor compared to the natural pollution, I would say, okay, we'd better know it. I mentioned the persistence of the metal oxides in the aerosol form. It can remain weeks or months. So here you have some contributions. Okay. Here is a table that I stole to a colleague of mine called Loïc Miraud, who presents the effect of various compounds as a function of altitude. Okay, so here you see black carbon, so this is a soot, alumina, water vapor, NOx, and so you see, depending on the altitude, the effect expressed in equivalent CO2. Okay. The CH4 methane is 28 kilo per kilogram. So 1 kilogram methane has the same effect as 28 kilogram CO2, whatever the altitude. The CO is 1.57. What's important to note are those, I think, here, which means that even at very high altitude, black carbon really creates a kind of layer blocking the process, inducing a warming effect with an effect which is much, much, much higher than the classical CO2 effect. Same for the alumina. Here are some curves also giving the time scales. So we can say that these elements, the criticality of these elements, depend on the species and the time scale. And this time scale themselves depend on the particulate sizes. So you see some examples here where we see that they can remain years or 100 years, okay, with their impact here. And here you have some simulations that were done by TRW in '94, showing the drop time, the re-entry time of particulates as a function of their size. Okay, so here you have 100 micron, which is already quite large. 100 micron is the diameter of a hair. Okay, so it's large, yes and no. But then when you go to lower values, so 100 micron would re-enter relatively rapidly, let's say in 50 hours or so. When you lower the size, 10 micron, 1 micron, then you start counting in thousands of hours. When you go to 100ths of micron, I'll let you make the conversion between what is 1 million hour in terms of number of days. So you see that the effect, once again, when you have a re-entry, you can expect that you may have some effects for months, years, maybe a decade after. Here is another example, which was done by Slimane Beki from Latmos in the frame of the ATISPAD study. He's a product. Here they simulated a re-entry, here a large re-entry, 20-ton spacecraft here. And so just one day after, here is the peak ozone loss. Okay, so the stage re-enters, the spacecraft re-enters at this place. 2 days after, it is a little bit spread. 3 days after, 4 days after. So you see that you have a kind of diffusion of this effect. So it means that, of course, what will count is a number of re-entries. For instance, if we look at SpaceX, you may have 1 or 2 re-entries like this every week. Okay, maybe even every day, but that's not. So this is something which is very important. Now, so these elements may lead to atmospheric pollution. If we look at the current contributions, even this, it's complex to know what are the figures. So this is why we say roughly 90 to 180 tons per year. Why is it so wide? It's because it's not only the orbital reentries. Also, you have some suborbital reentries. If you go above 100-kilometer altitude and you're reentering, okay, it's not orbital velocity, so the effects will be smaller, but nevertheless, you have it. And the lower stages are much larger than the orbital stages. So depending on if you include all the suborbital launches or not, that's another thing. So yes, I mentioned it here. You see, so we can have 900 tons per year when we include the suborbital stages. Then what we consider today is the demise of a typical 250 kilogram satellite can generate around 30 kilogram of aluminum oxide nanoparticle. What is a 250 kilogram satellite? Oh, strange, it's the Starlink 1. Okay, so the typical Starlink 1, I remind you that today, as per today, they launched, I think, 8,000, out of which 1,200 already re-entered. And anyhow, the 8,000 will re-enter within 5 years, okay, because they have a lifetime of 5 years, and they re-enter just at the end of lifetime in a couple of years' time. So all the Starlink constellation, where the first phase will be 12,000, the second phase will be 42,000 satellites, will re-enter, okay? And will generate this kind of impact that we have from alumina. If we try to compare with the natural influx, so the natural influx is much higher, 6,000 to 25,000 tons per year, okay? Nevertheless, it's not the same materials. And so if we look, for instance, just at the aluminum itself, you don't have, I'm not expert at all in the meteorites, but there's much less aluminum than in the spacecraft, okay? So it means that already today we have 30% aluminum re-entering, which is anthropogenic, which is not the natural one. 10% of the stratospheric aerosols measured contain re-entry metals. So today we really have a significant lack of consolidated, coherent, reliable data. The problem, of course, is that what will happen in the future. So I'll remind you just quickly, 10 years ago we had roughly 1,000 active satellites. Today we have 10,000. By 2030, we'll have between 30,000 and 100,000 satellites, depending on whether we're optimistic or pessimistic. And all these satellites are basically in LEO and will re-enter. So the question is really, what will happen in the future? So you have the two elements here. And clearly, we can identify that we have a dilemma here. Should we give the priority to the casualty risk minimization, or should we give the priority to atmospheric pollution? Okay, do I want to stop killing people or stop killing atmosphere? Okay, that's a good question, good valid question. So if we look at the casualty risk, so far we've had 32,000 re-entries, never a death, never a wounded people, never even. We've had one which was hit, but very, very slowly. It was Lottie Williams. Here is a curve produced by ESA, so it's quite old, but if we extrapolate, we could say that typically today, statistically, we should have had 2 deaths. Okay? So it's not 0, it's not 2,000. I mean, so it's 2 deaths. Why not? We've seen no deaths, no wounds, due to the fact that 71% of the Earth's surface is water. Then we have 20% of deserts and forests. The inhabited zones represent only 3.3% of the globe, of the surface of the globe. And then our models are very conservative. I mean, for instance, if we had a debris falling on the roof, I think that the Rolex Center has a good architect, so no one would be hit. Okay, and so on and so on. So probably the 14 joules that we are considering also is very conservative, and so probably our evaluation methods are too conservative. On the atmospheric pollution, there is no evidence yet that it can be problematic. When we compare with natural environment, it's complex. We have orders of magnitude. To be very honest with you, in some articles, we even see that some reentry can be beneficial. So then I'm puzzled, I scratch my head and I say, okay, we need to do more work. Okay? But then the effects such as the ozone holes that we know quite well, it was from the 70s with the fluor composites, it takes quite a long time to recover. So if we can avoid it, that would be good. Maybe we need to adopt a precautionary principle. Maybe we need to keep in mind this notion of long-term sustainability. And once again, Emmanuelle, thank you for inviting me to promote this. Okay, and so this is my last chart, I swear. We consider, the authors, we consider that priority should be given to the atmosphere. Okay, so who cares about killing someone once in a while, if ever? Okay, we need to be cautious with the atmosphere. We need to be sure that we are not doing something that will take years or decades to recover afterwards, and don't play the apprenti sorcerer. I mean, we need to be careful. That's very classical for it. So we are promoting something which is completely out of the classical ways of thinking. We are promoting the D4ND, design for non-demise. Okay, precisely select architectures and materials that survive atmospheric reentry. If I take again my example, if I have the choice between a tank in titanium and then one in aluminum, let's take the titanium one because I know that it will survive at reentry. We select the shapes in order to minimize also NOx production. Of course, then the best thing is to associate it with a recommendation to perform a controlled reentry over an inhabited area. That's good because that's exactly the sentence which exists in every single standard from debris. Of course, the ESA, the ISO, NASA, CNES, and so, but also even the Chinese one, for instance, has a sentence saying, at the end of a mission, you shall do a controlled reentry in order to be sure that you don't kill someone. So, now, what does it mean to do a design for non-demise? We don't know yet. What can be the impact on the economic side, social, safety implications? So what we propose is to stimulate more research on the topic, coordinated at the worldwide level, to do some simulations, okay, refine this. And we need the good experts in atmosphere, for instance, and things like this, okay, because refined ablation, atmospheric chemistry, high atmospheric chemistry is something awfully complex because you have recombination and plenty of things. And of course, we are completely incompetent on the subject. So do some ground-based measurements, analyze the ablated products, the NOx production, the CFRP, including the black carbon. For instance, in Maia, we plan to have some measurements of the plume during the ground tests, okay, to see what comes out of the engine, mainly in terms of soot and so. Same in situ measurements, conduct aircraft, sounding balloons, but sounding balloons, they stop at 25, 30, 35 kilometer altitude. So all the ignorosphere, which is between 40 and 100 kilometers, it remains unknown. So what we could do is to have other means of measure. And for instance, in Maia, we plan to have some sensors flying every time we fly, okay, every time we have a launch. For instance, the first stage is reusable, so we will have a box with some measures and fly it every time and see what comes out of it, okay. And last thing, one thing which is very important and which is raising today is a working group called the AIRL, Atmospheric Impact of Spacecraft Reentries and Launches, which is chaired today by European Science Foundation and ESA, but in which we have EU, NASA, NOAA, CNES, DLR, LATMOS. LATMOS is a French laboratory specialized in the atmosphere. We have Académie de l'air et de l'espace, which is strongly supporting it, and so on. So this is something which is very positive. We hope that it will give the impetus, but we are starting. Okay? We're at the stage where we just exchange references, and that's all. And of course, in parallel, we must continue to lead some other possibilities at system level, such as recovery, reusability, recycling, in-orbit servicing, and so on. So this is something that we need to do now, because all the mega constellations are there. And thank you very much for your kind attention.
Thank you.
And the presentation is available to whoever wants it. I think, Emmanuelle, you have it. Or, okay.
Thank you very much, Christophe, for
You're
this
welcome.
very interesting, scary presentation as well. Please take a seat, and
thank
you will be joined by our panel, which I kindly invite to join us now on stage. Please, I'll take this, the last one. I'll present you. Come with me and take a seat. Any seat, I'll take this one. So, we are lucky to have with us tonight 3 additional speakers from different continents, which I'm very happy of. I'll start with you, Dr. Susmita Mohanty from India. You're a spaceship designer, currently Director General of the think tank Spaceport Sarabhai. You're holding 4 master's degrees and 1 PhD, and you have a long career as a space entrepreneur, having co-founded 3 different companies on 3 different continents, US, Europe, and India. And as a space engineer, you also worked on the International Space Station program. We also have Lisbeth Kezier, who currently is the lead of public procurement and sustainable infrastructure at the International Institute for Sustainable Development, based in Canada, headquarters, but with a big office here in Geneva. The IISD, is a global think tank that works on sustainable development solutions for a stable climate, sustainable resources, and fair economies in more than 100 countries. And you, Lisbeth, you lead the work on sustainable infrastructure, focusing on how to plan, procure, value, and finance infrastructure projects that deliver benefits to the people on the planet. And finally, we have Athanasios Nenes, a local, if I can say that, full professor here at the Laboratory of Atmospheric Processes and their impacts at EPFL. So, as said, we'll have a discussion first amongst us, and then you'll have the opportunity to ask questions. So please already do. You have the QR code, scan it, ask your questions, and I will redirect the questions, which should appear here on the iPad to the speakers, but a bit late. Yeah, please take a microphone. You have each. There's 3 for 4, so you can share the microphone. But first, we'll start by building a bit on Christophe's presentation, and the first question might be to you. Well, this is a kind of challenging idea, this designed for non-demis. I was curious to know if it's well welcomed by the space agencies, by the space companies, because it's a total shift of paradigm, if I can say that, in terms of building the spacecraft.
It's a very good question. It's brand new. I mean, it was first presented.
Please put your mic. Yeah, here we go.
It was. It was first presented in a workshop in December in Hong Kong, where Jean-Paul was attending, and so since this, it's percolating slowly, and so we received plenty of positive comments. And, oh, that could be interesting, but okay, it means that and so we are working on this.
So what are the buts? But what are they?
Oh, but it's expensive. It's more expensive. It's more complex to do. It's to guarantee that something will not melt is at least as complex as to guarantee that it will melt. In terms of course, the basic hardware itself, you can guarantee if you take titanium, for instance, it will not melt. But then titanium will be attached, will be bolted to other structures. What happens at the interface? How does it behave? And so, but these are the open points that we identified so far. And then economically, it's complex. It has to be clearly associated with the controlled reentry. And for this, we are one step beyond what was done so far. Now we are more and more considering, okay, very briefly speaking, today when the international rules say that when you launch something, it shall re-enter within 25 years. Okay? But this 25-year rule was approved in 2002, so when there were no debris. And so now we realize that we need really to change it, and to change it to 5 years or maybe 1 year, and maybe 0, but 1 year. And so the idea is to say, if we specify to spacecraft, you must re-enter in 1 year. It means that they need to have much more propellant on board and much more a more serious engine and so on and so on. Then they yell saying it will cost awfully much and so. But then we say, yeah, but 25 years is not serious. So one compromise would be to say, okay, you re-enter in less than 1 year, but not by yourself. Meaning there will be services, in-orbit service, where you will have a service vehicle coming to fetch you at the end of life. Okay, and so it means that then if you're a designer of a satellite, well, I don't care anymore about propellant. Someone will come and fetch me.
We'll come to that.
Yeah? Okay, sorry.
Come to that.
Okay. So this is directly associated to this idea of design for non-demise.
We have a space engineer with us. So what do you think of this idea? Oh, please take a mic. Actually, you can keep the mic because Christophe.
Yeah, I think we all three have one. I didn't know, for example, that it was in 2002 that the 5-year rule was, because now it doesn't make sense anymore.
Yep.
So I think when it comes to LEO, mega constellations, it's definitely quite problematic that a single company owns 2/3 of the operational satellites in low Earth orbit today. And we have other mega constellations as well. So one of the ideas that we have been debating, not at a country level, but think tanks and so on, is should the LEO have a similar regime in terms of regulations as GEO, where an international body like the ITU allocates orbital space? Because the whole idea of a global commons comes to naught if a handful of companies and countries control all of this. Would you call LEO up to 2,000 kilometers, yes, Christophe? So I think that's hugely problematic. And if I give you some numbers, I looked up India's space traffic management report from 2023, and there were about 137,000, roughly, close call alerts given to the Indian Space Agency from the US Space Command, and they had to do collision avoidance maneuvers. So 140,000 a year for a country like India, which has about 21 satellites, it's early 20s in LEO, about 29 in GEO, is a lot of maneuvers in a single year, just to give you a sense. So I think we need some sort of international body allocating space.
So let's stick on this, maybe with you, Lisbeth. There's no treaty now, punishing anyone polluting the stratosphere. So on what level should that problem be tackled? Is that international? Is that local, national? Is that through the agencies? I mean, ESA just brought its zero debris charter recently in 2030. So at what level should it be tackled?
Well, actually, it would need to be tackled at a combination of all those levels. I think the main challenge is in relation to the global commons. We need international cooperation, international governance, and the main treaty that regulates that, the Treaty on Outer Space, this dates back from 1967, and that was a time that was completely different when we look at space activity today and back then. So the main challenge is that's a treaty that's entirely outdated, though there are of course high-level principles in there that still apply. But the challenge is on how to reform such treaties in a way that different UN member states and ideally all UN member states can sign up to. And I think that's really the core of the challenge when it comes to regulation of space and the commons.
So we saw that the pollution has impact on the ozone layer, and we'll come back to this in a second with you. Before that, there's one treaty tackling the problem of the ozone layer, which is the Montreal Protocol, sorry. Can we just extend this protocol with this new problem?
Yeah, so actually when listening to the presentation, well, ahead of the presentation, I had prepared in my head if I need to give maybe one success story in international public law and environmental regulation, it's probably the Montreal Protocol, because we dealt with a very specific issue, but there was also a lot of scientific consensus on what the issue was. There were readily available alternatives that were cost-effective, and that was actually one of the reasons why the Montreal Protocol was successful. So it's an interesting question on can we extend that to cover these issues as well? In theory, of course, yes, but I think some of these elements, and again, that's also a protocol that dates back to the 80s. Yeah. So we need to, I think, follow the professor's example of making sure that the knowledge and the scientific uncertainty gets not fully resolved, but gets that the knowledge gap gets closer to be able to do that and to take that step.
Yeah, so, Professor Nanès, the knowledge gap, Christophe said we know nothing. Do you agree?
We know very little, that's for sure. I mean, we hardly have observations to start constraining the models. The thing is that to formulate policies, you need to have enough knowledge so that you can formulate science-based policies, not just say we take at random 10%. We have to really have knowledge. And so that means there needs to be experiments, there needs to be campaigns to observe the upper atmosphere. We need to quantify better how much actually material remains, for how long. The size distribution of particles is critical. And understanding each type of satellite, what kind of emissions are produced. Then you can actually start thinking about putting these in models and understanding the policy.
So we have the tools to do that. We have all the tools we need to establish this pollution very
We have some initial tools, so we do have models that we can use. They're used also for climate prediction, used for weather, so those can also be retrofit to include these kinds of sources inside. But what's lacking a lot is the data required to understand, for a given satellite, how many particles are emitted, the vapors that are emitted, how long do they take to oxidize to form particulate matter, in which form, and then what are the impacts? Like, for example, we say that they can deplete the ozone hole. Yes, we know, but I mean, for the efficiency of the particles depends very highly on how it's been processed in the atmosphere, how efficiently they can deplete the ozone hole. Some of these particles can make clouds. Those are polar stratospheric clouds. Clearly, they can really deplete the ozone, and we know that. But other things can also be impactful. They can also affect weather clouds because they can fall into the lower stratosphere and start impacting things like rain formation, etc. So there are many, many implications of these particles.
So clouds, Christophe even was provocative a bit by saying this could diminish the global warming effect because by forming new clouds, you diminish the light?
Yes, absolutely. They can reflect sunlight, and that's one form of radiation management, geoengineering. But the other impacts that could be negative are something that also that we are not aware of, and they can outweigh by far whatever benefits you have to climate cooling. And honestly, cooling the Earth continuously is also a problem because you diminish the solar radiation that's available for things like crops, etc. Yeah.
Would you say there's the will, the support to do such research, or that it's still, very at the beginning and everybody's looking at each other?
It's a big knowledge gap. It's something that in the upcoming decades, we know there are going to be a lot more satellites in there. I mean, just what's planned already is an immense amount of material that will come down. So that is a great motivation to start understanding what to anticipate.
Let me turn back to you, Lisbeth. You're working on the so-called planetary boundaries, so a lot of ideas to do better in terms of sustainability. How can we apply what you do on Earth for the planetary boundaries to space? Is there a link? Is there something that we can translate?
Well, I think there are lessons to take from how we have mismanaged development on Earth in the sense that we haven't taken into account what we call the planetary boundaries into human and economic development. And in our work on infrastructure, what we see most as being problematic is there's no long-term planning, whilst infrastructure investments have a huge lock-in effect. What we build today, it's very likely going to be there in 20 years' time or in 50 years' time. What we also don't factor in when we design infrastructure is to take life cycle approaches and to actually try to think more circular, which is actually something that in the environment of space I hear quite a lot about. Again, there's lots of complexities on how to do that, but I certainly think that we need to move away from thinking linear and really try to see how we can apply these concepts like a circular economy also in the space environment. Because ultimately, even if some resources might not be finite, we are entering, we've for decades used resources unsustainably, and so not factoring in that time perspective of when resources like forests, water, etc., when that regenerates, when that gets cleaner, ultimately will have a huge impact and has already today an impact on human health and economic development. So factoring in the risk factor, I think, to the point is, I think that's what will create ultimately also the will to really address the issues.
Well, if I may be provocative, we're just amongst us here tonight. No, we have a launch tonight. You might know that, Starship 9, if I'm correct. We have someone behind SpaceX that actually, does he care about what you're saying? The question is, how do we bring the commercial sector as well in all this discussion? Because we can agree that on the state level, with more consideration for sustainability or pollution or environment, it's okay. But what about the commercial part? How do we bring this commercial part sector as well on board? I don't know if you...
Are we targeting Starship? So I think when you look at the fact that a quarter of a century into this millennium, the private companies have as big a role today as the government companies. In fact, it's starting to exceed, if you ask me, in the case of Mr. Musk and NASA, it's almost getting close to the tail wags the dog, as we would say, the English phrase. So I think we definitely need commercial participation in a good way. But I think when the owner of a company claims that Starlink, for example, is more of a social enterprise, empowering people, while the reality is there's the other side of the coin, which is it's an empire-building tool. And I think the geopolitics of space is a very delicate matter which needs to be thought through, and I think multilateralism is on the decline, minilateralism is on its way up. So I think we do live in explosive times, pun intended.
You wanted to add something?
Yeah, I fully agree, and we need to be, I think, extremely careful in understanding what's the current balance and what's a better balance between the commercial activity and the state activity in space, and that's the same on Earth. We see that kind of exploitation of resources where the checks and balances are gone on multiple levels.
But what could be the incentive for commercial entity to act and agree with what you say? I mean, on the state level, again, it's...
So I think there are two things. One is that we do see, and again, I can't speak necessarily for space actors, but on Earth, infrastructure developers, for example, they do see the risk of not taking into account climate impacts, for example, if they're the owners of infrastructure and they don't take into account how resilient their design, goes back to the design of what we develop, if they don't take into account it, they will carry the cost of that. So I think increasingly there is knowledge, and we need to develop knowledge on how that risk can get factored in. And then I think there will be a role for regulation, inevitably. Regulation also provides some the right regulation provides certainty and predictability, and that can open a space in which more actors can become active.
There was actually a paper published last week by, and one of the co-authors in that room, or even two of the co-authors are in that room, Emmanuelle and Jean-Paul Kneib. They just published this paper in Acta Astronautica about the so-called space sustainability rating, which is a tool that could actually rate every mission. But again, would that be accepted by those, launching those missions? This is a kind of very nice theoretical tool, but on the ground of practice, how would you comment on that? Christophe?
It's a complex question. Thank you for raising it. I think there are several things. To be very high level, one of the questions is the use of space. How do you justify the use of space? For instance, Elon Musk considers that he's a savior of humanity because he provides internet for 4 billion people. So who cares about polluting a bit? You see, this is or even we define as space debris as something which is artificial, orbital, non-functional. What does it mean? When we discussed with Peter Beck from the New Zealand launcher, he launched a very nice disco ball in space, 1 meter size, completely passive with different colors and mirrors. And when we told him this is purely dumping debris in orbit, and he said, no, it has a function. It gives me a good publicity. For instance, without it, you wouldn't talk about me. So we had, during 3 years, we had an action at IDC level trying to restrict and give some rules and somewhere be capable of saying, no, this you cannot do, or this you are allowed to do. And it failed. It failed because it was purely subjective. And so today, I must say that if I want to launch tomorrow my washing machine in the middle of Starlink, I'm allowed to do so. Okay? I need to find a launcher who will do it, but
you're building one, so.
But there is a lot of pushback in international fora that I attend. There's a lot of pushback not only from these mega corporations who own these mega constellations, and people. I remember being on a panel in Riyadh last autumn. And the moderator asked people on the stage, what do they think of the fact that a single company owns 2/3 of the satellites in LEO? And every single moderator, being in a position of power, heading companies and United Nations and other things, everybody dodged the question. So I think who will bell the cat is the other challenge.
No.
Okay. Two figures just to add very quickly. You must realize that 62% of the satellites in orbit are American today, and 97.5% of the debris in LEO are US, Russia, China. Okay, and so the people to convince, unfortunately, it's not you, it's not us today, it's the 3 other ones. And so United States, we know how it turns. Russia, they hardly discuss. And China, as I say, that they behave absolutely perfectly, and they're 100% compliant. And so every time we tell them, this was an anomaly, but don't worry, it will not happen again. And so this, internationally, it's quite complex.
So you were talking about big companies. Let's talk now about startups, small companies. You mentioned one, or was it maybe Emmanuelle? ClearSpace. Trying to launch this robot that would drag one of the Vega C parts and burn it down in the atmosphere. But that's just one part. So the question is cleaning space an opportunity, a possibility? And this brings us to one of the questions of the audience. So it allows me to kind of distillate the questions of the audience as well. Is there finally a business case for sustainable space?
I think there are several hurdles. we all understand that we must do some active debris removal, okay, without entering into the detail, but we should remove typically 10 large debris every year from the crowded regions. And this raises plenty of problems. First, technical. How do we do so? Then financial. How do we finance? Then it's a dual use. How do I guarantee? If I'm capable of deorbiting one of my debris, I'm capable of deorbiting something which is not mine and not a debris. Okay, and what about the insurances and so? So, ClearSpace answers to the first question, which is technically, how would we do? And these claims and so. And I would say, but this is my personal opinion, the size of the debris doesn't matter really. The thing is really, how do we do the complete chain of going and catching something and demonstrating that we can do so? I'm 100% sure that if we can do it on a 100 kilogram debris, then it's easy to do on a 2 tons debris afterwards. Then the questions are, how much does it cost? ClearSpace, today, I'm not sure that they will answer to this question easily. And what are the insurances and things like this? Today, it's an ESA object in a mission financed by ESA. But for instance, just me, I tried to see with Maia, if I want to go and fetch a French debris, I may not even be allowed to do so, you know, because it's not because I'm French that I can go and touch a French debris, which does not belong to me directly. And so these are real hurdles.
And the third question is, who should pay? Or maybe the question from
you, of course. No. So for this, if I have 2 minutes, we have studied 5 ways of financing this, and it has been published. So if you're interested, just ask me. So at international level, or tax raising, or okay. The 5th one is the most promising one. It's what we call the in-orbit servicing. So we have a vehicle, we're talking about tomorrow, or the day after tomorrow. You have a vehicle which is capable of doing plenty of things in orbit. On Monday, it goes and refill a satellite. On Tuesday, it moves it from one place to another one. On Wednesday, it repairs it. On Thursday, it changes, things like this. And on Sunday, it must comply with the international rules and deorbit itself in a controlled way. So we tell them on Sunday, okay, when you deorbit, please grab the nearby debris and take it with you. And so the cost, in this case, becomes marginal. Because, first of all, the service has been paid by all the other customers, the one who wants to refill. The chaser is already equipped with everything to do a rendezvous, maybe an arm, and so on and so on. So it's not zero, but the cost becomes marginal. So
but are there any companies, Christophe, that are which have a business case for in-orbit service, repair, and maintenance and deorbiting?
MaiaSpace, for instance.
Okay.
This is a thing that, so, okay, I knock on wood. Okay, I don't know if it's wood, but this is clearly some things that we're aiming at. We have a motto, for instance, 1 up, 1 down. Every time we launch a significant satellite, we have some performance reserve in the kick stage, enabling us to go and fetch a debris and deorbit it with us. Okay, so.
Can I say something about the Indian startup? So in Bangalore, for example, we have a startup called Bellatrix, which is working on green propulsion. So how to steer away from hydrazine-based propellants, and also they're working on electronic thrusters. There is a space situational awareness focused company called Digantara. We don't have any in-orbit servicing, maintenance, repair companies yet. But I think what's very cool is that countries which are not responsible for creation of debris, such as Switzerland or Japan, are the ones trying to think of ways to clean it. And the ones which are just sitting around and, you know, pushing back. So that's the irony of the situation.
Thank you. Time is running so fast. I'll take some questions from the audience now, and they come as they are. Limited knowledge plus precautionary principle equals launch moratorium until we learn more. Who agreed with that?
Moratorium would be a problem, but the limitation, yes.
And one for you as well, Professor Nellis. If you had unlimited funding to focus on just one aspect of environmental and chemical impacts of space debris deorbiting, which area would you prioritize?
That's a great question. I'd prioritize the aerosol generation from burning of the debris as it enters the atmosphere. That's a key thing that really has impacts.
The one on the Outer Space Treaty we already had. Let's come to your second point. I know it's important to you. We didn't address that about sustainability. When we speak about sustainability, we speak about exploitation of space resources, space mining, and this is the Far West in space for the moment, right?
Yeah, it's definitely a topic which is very close to my heart, having spent 15 years in human space exploration. So I think one of the big concerns we have is the moon, as in the Earth's moon, is currently in the crosshair of every spacefaring country in terms of exploration. So many of us are concerned that resource extraction on the moon could potentially happen, and what are the laws governing it? So if you see, in November of 2015, the United States Congress passed a law for US resources, whatever, exploration and exploitation, which allows American companies to go out and bring material from celestial bodies and own it as a country. In 2017, 2 years later, Luxembourg passed a similar law for asteroid mining, because I think Luxembourg wants to be the Bahamas of space resource mining and provide legal and sort of commercial haven to companies. There's the UAE, which is also talking about a similar law. And 5 years after Obama, Trump 1.0, Trump passed an executive order. And just because I think I have it here on my phone, I would like to, it's pretty short, but it is extremely, and if you know, in Trump 2.0, he's now allowing deep sea mining, which is going to be extremely problematic. Let me just read a couple of sentences from the executive order, and I'll leave it to the imagination of the audience. So the executive order passed by President Trump during his first term says, as America prepares to return humans to the moon and journey on to Mars, this executive order establishes US policy towards the recovery and use of space resources, such as water and certain minerals, in order to encourage the commercial development of space. The order reaffirms US support for the 1967 Outer Space Treaty while continuing to reject the 1979 Moon Agreement. The order further clarifies that the United States does not view outer space as a global commons, and I will leave it at that. And the fact that the Artemis Accords, which are a bilateral tool that the US signs with multiple countries, and US wants to lead sort of the governance around moon exploration, I think it's extremely problematic at this point. And the Outer Space Treaty, as Elizabeth pointed out, was designed for the times and mostly focused on how to prevent nuclearization of space. It really has nothing to do to prevent things happening on the moon. And I think many of us in the exploration milieu are worried about what's going to happen.
There's one question that relates to this but is broader. I will just read it. Building on the idea of a launch moratorium driven by the precautionary principle, do you see a possibility for a tidal licensing or a green light framework? Could a global panel of or independent agency evaluate each launch based on its environmental risk and allow launches that meet a minimum sustainability threshold? How might this be structured and enforced? So again, it's about the organization of allowing what to go to space.
I think there is no idea of having orbital operations without polluting. Okay, you need propellant to go up, you need to manufacture stuff, you need to, so far we cannot recover the upper stages, and so we burn at reentry and so on and so on. So the question is, we try to minimize it, or we try, but we cannot stop it. And the moratorium is a good idea, of course. One of the main problems that I see there is you know that the environmental parameters, I talk under your responsibility, there are typically 50 parameters to define the environment of Earth. Velocity, speed of the wind, salinity of the water, and things like that. Out of these 50 temperatures, out of these 50 parameters, 29 are available only from space. Okay, if you want to measure the temperature of an ocean, you will not plant a thermometer every 10 meters. You need to do it from space. And so you need it. You need to know this and to monitor this. You need to pollute first. So
but the question was rather about the structure that would allow or not any launch with respect to a rating, for example, with the example that has been given in the
we're trying to progress.
A kind of FAA of the world, right, for launchers. Is that possible? Is that feasible? Where?
FAA may not be exactly a good example, but okay, that's a side effect. That's something that we're trying, definitely. That some countries, some people, some entities are really concerned about this. And you mentioned the ESA Zero Debris Charter. This is a good direction, of course. And, but it's a charter, it's not applicable, it will take some time before arriving. But, for instance, it's influencing, once again, I'm sorry, I'm selfish, but MaiaSpace, our stages are in stainless steel. They do not burn at reentry. So we have a design for non-demise. And we are and the propellant is biomethane, which is zero effect or minimal effect when you create it and so on. And so these are really the things that Antoinette is pushing us to look at. So this is in the good direction, but it's just we are a little bit cleaner than others. And not even we're a little bit, we hope that one day when we are able to launch, we will be cleaner. But,
Lisbeth, I'd like to hear on this structure too, because that's exactly your topic, but with planetary boundaries.
I mean, I definitely think that having ratings and tools and criteria that incrementally change over time as well, and trying to put them as like, this is the minimum of what we need to comply with, and then also having some ideas around what elements you might need to phase out, just taking inspiration from Montreal as well. They're a good idea. I think the challenge from what I'm hearing here is both still technical as well as, of course, political, right? And so I think that's where there's just a lot of work to be done. Also, in political will is part of it is created through public awareness as well. And I think what's good is today we see increasingly more media reporting on what's happening in space, what is potentially problematic in space, and what we might need in the future. If we think about how Montreal and how ozone was regulated, well, the public understood how bad the hole in the ozone layer was. It had a direct impact on human health. So being able to make those linkages is what can help us get there.
Wanted to add something? No.
Yeah, I mean, I think the Montreal Protocol was so successful because there was the smoking gun, there was the huge ozone hole, and the pictures made it so clear. There was a ready-made solution, DuPont had it, and there were a few actors that were responsible for the problem. So I think in this case, we do have a few actors that could be responsible for a huge part of the problem, a few companies, so that we have checked. We are still missing a smoking gun saying how hugely impactful this garbage can be. But, so I think our problem here is more like the nanoplastics problem. It accumulates, and it doesn't go away. So I think the public has to be aware that these impacts are not going to be like the ozone hole. Mm-hmm. They're going to be more like the plastics problem. It's going to be global, and everybody will suffer. And the impacts will be on many aspects of the atmosphere and the environment.
But it's going to be long-lasting, as you said.
It's going to be long-lasting. Stuff that you put in 40 kilometers can stay for decades. There's a volcano that erupts and puts particles in the air, and that cools climate for years. Well, imagine this going on continuously, in an increasing rate. That's the problem.
And that's the problem, because that's the same argument with the climate change. I mean, it's
exactly.
long-lasting, it's incremental, nobody sees it, but nobody cares at the end.
until it starts slamming in your face with hurricanes and tornadoes and extreme events.
Yeah, I think it's the dictatorship of the eye. We humans, of all our sensorial faculties, I think the ozone hole really caught the public's imagination because they could kind of see it. Not literally, but they could see it. And I think until we have an episode from space debris that they are able to kind of visualize and assimilate, I don't think there is much change. And speaking about the Montreal Protocol, I think we should also mention the Antarctic Treaty of 1959, which I think is a great example that we should sort of extrapolate to the moon. Whether it will work or not is another matter, but I think it's a great example.
We closely,
Just for a joke, but Antarctic, okay, it has been evolving. Now you have airplanes going, landing in Antarctica to make some tours. So you see? Yeah, so this is new. Okay, exactly. So this is a natural tendency. Sorry.
There's an interesting suggestion here regarding tonight's launch of Starship, which is made of steel mainly. So to be brought back and reused. Actually, tonight is the first launch with the reuse of the main tank for the Starship 9.
I have a question for Christophe.
Yeah, let me ask mine. So there's this suggestion to reuse satellites. Is that a possibility?
Yeah, the problem is to bring it back to Earth. And we spent a hell of energy to get it up there. Now it's awful to get it back. And
but could we reuse parts of those satellites?
Yes, we could. So we have been studying a lot all the recycling possibilities. But typically, to get a satellite, to bring back a satellite on Earth, we should ask Claude about it because he did it. And it's awfully complex. You need a shuttle. You need a system with thermal protection to bring it back. And then, if the satellite is a little bit old. Typical satellites in GEO, for instance, they last 15 years. Well, after 15 years, they're not. You'd better launch a new one. I mean, if you look at your smartphone, you will not reuse it in 15 years. So, so the reuse on ground. Then we can try to recycle in orbit. Unfortunately, in orbit, it's complex because they are not in the same orbit. It's not the same inclination, same altitude, same longitude, and so on. So the cost of bringing A to B is awful. But there are some possibilities. And so the most basic reusabilities that we found was just to cut big chunks of dead satellites or dead launchers, to melt them a little bit and to extrude them to make some material for 3D printers. You see, so.
You wanted to ask a question quickly because we're
running just a quick
late.
question for Christophe. So they're talking about deorbiting the International Space Station in 2030. Can you help me visualize how the deorbit will happen and what will burn, what will hit the ocean floor?
Oh, yes, we know it very well. We know it very well because it has been done in the past with smaller stations, but basically the same kind of station. I mean, there was the Mir space station, if I remember well, it was 2001. Before this, we had Skylab, we had Salyut 7. Okay, random reentry, it spread plenty of debris in South America. But so we know this process, we know how to simulate it. And
but what portion of it, what percentage of it will hit the ocean floor and what will burn up?
I think 20%, 30% will survive reentry, but will be in this powwow and then close to the Nemo if everything goes fine. Okay, but it will be in South Pacific, so no victim, no. But it's a complex mission.
Unfortunately, we're running late with questions. I know there are some questions unanswered, but I'm sure you will have time at the apéro to answer them. I have one last question for each of you, which is from the audience as well. I'll modify it a bit. What are, in your opinion, not three, but one action that could be taken today by a satellite manufacturer or provider, operator, in order to reduce atmospheric pollution during re-entry, while not compromising the safety of people on Earth? So what is your one advice or recommendation, wish? Starting with you, Christophe.
Very easy. Do what is written.
Meaning?
We have plenty of standards, laws, rules, guidelines, code of conduct, and things like that. Please apply them, at least. Today operators spend more time trying to avoid and seeing how to waive the rules than to do so. I think that we have 60% or 70% of the space operations which are not compliant. Okay, so,
Lisbeth, one wish?
I mean, I think for me it would be to really look at the design phase of those missions and then what happens and take that life cycle approach to really understand what the impact is and to try to close some of the knowledge gaps.
The scientist's view?
Try to use materials that upon re-entry, they don't emit as many particles and compounds that are harmful for the upper atmosphere. That we know.
Yeah. And Dr. Mahanti?
Don't try to take over the world. Think of smaller constellations.
So that's going to be a big wish with tonight's launch. So thank you very much. A round of applause for our speakers. Thank you very much. As said, there's an aperitif for all of you to ask more questions to the speakers. Please take this opportunity as we are just amongst us. And thank you again.
thank you, Olivier. Thank you to the organizers. Excellent.
Yeah, leave them.
Thanks.
You can leave them there.
Thanks a lot.